Very good. That is really dog and bugs. Genius.
G'day and welcome back to Mathematics for another Extension 2 maths lesson. We're starting off with a flashback question from the proof topic. It's an inequalities question asking us to prove that for positive numbers a and b, a plus b times 1 over a plus 1 over b is greater than or equal to 4. By all means, pause the video and have a go yourself before I run through my solution. Alright, first thing I'm going to do is just have a play around with the left-hand side and see if I can get it to look like something that I can work with. So if I expand out the two brackets, I have a over a plus a over b plus b over a plus b over b. Now a over a and b over b are of course equal to 1. So now looking at this, I see a over b plus b over a, and I recognize that as something that I can work with from questions I've done before on this channel. So straight away this tells me where my starting point should be, which is a minus b squared greater than or equal to 0. We know this as a true fact, so we can start here as the basis of our proof. We're going to expand the left-hand side as a perfect square. We're going to add the 2ab across the right-hand side, and then divide both sides of the inequality by ab. The reason we can do that is because we know a and b are positive, so we know that the sign does not turn around. So dividing everything by ab, we end up with a over b plus b over a is greater than or equal to 2, which is good because now I know this part is bigger than 2, which means if I add 1 and 1 to it, it's going to be bigger than 4. So that's what I'll do. I'll add 1 and 1 to it. Now the right-hand side is greater than or equal to 4, and now I can factorize the left, and I have my target, so I write a big fat QED, and I move on to the next question. All right, today on the channel, we're starting our next topic for Extension 2, which is all about vectors. Hopefully something you have some experience with from the Extension 1 course, but in Extension 2, we take it just a little step further, such as looking at three-dimensional vectors, which is what today's lesson is focusing on. Okay, like I said, hopefully from the Extension 1 course, you are roughly familiar with the concept of a 2D vector, something with a direction and a magnitude. Here's our two notations, a column vector or a vector in component form, where I and j are your unit vectors going across and going up. All right, in Extension 2, we extend this into a third dimension by adding a third component, which we call the k component, okay, or the z axis. So imagine your x and y axis is like a piece of paper on a table. The z axis is coming off the table, perpendicular to both x and y. All right, so our notation, we have three numbers in our column vector, and like I said, our third component for the z axis is k. So that's our unit vector in the z direction. Okay, today we're focusing more on using vector results, like similar formulas we've seen in Extension 1 and seeing how we apply them in Extension 2, which thankfully is very similar. So today shouldn't be a massive stretch of the brain, it's just practicing some skills that should hopefully already be a little bit familiar. Okay, here are two generic 3D vectors A and B. Now, just like in Extension 1, we know that vectors are parallel if one of the vectors is a scalar multiple of the other. Okay, so if I can take A and multiply all three things by 5 and get b, it means that the two vectors are parallel. If one is just a scaled up or down version of the other. Okay, the magnitude of a vector, very similar to in 2D where we do Pythagoras. In 3D, we're going to do 3D Pythagoras. So the magnitude of a 3D vector is the square root of the components squared and plus together. And of course, if you want to find a vector from A to B, all you need to do is do point B, take away point A. Okay, so it's a very useful formula we can use a lot in the next couple of videos. All right, some more results. The scalar product, or aka the dot product, is the same as it is in two-dimensional. We just multiply the x, y, and z terms and then sum together the results. Okay, there's our dot product. The angle between two vectors formula is still the same. If you want to find the angle between A and B, where the angle is theta, we can use this formula relating cos theta, the product of the magnitudes, and the scalar product. Often we'll be rearranging this to have cos theta equals dot product divided by product of magnitudes, but yeah, nothing you haven't seen before. And the projection of one vector onto another, the formula still holds in 3D as well. So the projection of a vector A in the direction of vector B, we do the dot product of the two vectors divided by the magnitude of b squared. That'll get us a number, and if we multiply that number to vector B, we get the projection of A onto B. When we do an example with a projection later in the lesson, I'll talk more about what a projection is if you're a bit rusty, but for now, yeah, formula still works. And this right here is just an alternative version of the formula. It does the same thing, but looks a little bit nicer. So yeah, some people are more familiar with this than this one, but I probably think this one on the right is more straightforward, personally. Okay, for our first example, we want to find a vector which is parallel to this vector u, but we want it to have a length of 5 units. Okay, a vector in the same direction as this, but with a length of 5. Okay, for this first one, the easiest way to handle this guy is to turn u into a unit vector, which means we're going to give it length 1. Okay, if we can find a unit vector which is parallel to u, all we need to do is multiply that by 5, and its length will go from 1 to 5, and then capiche, we've answered the question. So first thing to do is find the magnitude of this vector so we can divide by that number and turn it into a unit vector. Okay, so first thing is the magnitude of u, square root of 2 squared plus minus 2 squared plus minus 5 squared. This works out to be 33, so the length of this vector u is square root 33 units. Okay, that means if I multiply u by 1 over root 33, which is kind of like I'm dividing by root 33, this is now a vector with length 1. Okay, the way we notate that is we write u with a little tilde and we put a little party hat on it. So that little hat on it there means it's a unit vector with length 1. Okay, now we have that. Like I said, all we need to do now is just multiply this vector by 5 and its length will go from 1 to 5. So there is our vector, which is parallel to u, but instead of having length root 33, it has length 5 units. Ta-da. Okay, for our next one, we have 3 coordinates in 3 dimensions, p, q, and r, and they form the vertices of a triangle. We want to show that the magnitude of the vector from r to p is equal to 3 times the magnitude of the vector from r to q. Okay, so to find these magnitudes, first thing we need to do is find these vectors. So we're going to use that formula from the start of the lesson, where if you want to find the vector from r to p, the quickest way to do that is do point p, take away point r. Okay, so rp is point p, which is 6, 3, minus 4. Take away point r, which is 2, minus 1, 3. If we work out this subtraction, we get 4, 4, and negative 7 as our vector from r to p. Now we'll do the same thing from r to q, so we'll do point q, take away point r, which looks like this, so q take away r. We end up with 1, positive 2, and negative 2 as our 3 components. Okay, now we have our 2 vectors. Now we can find the magnitude of these vectors and see if one is 3 times the size of the other. So first of all, finding the size or the length or the magnitude of RQ. So we're doing the square root of 1 squared plus 2 squared plus minus 2 squared. This works out to be the square root of 9, which of course is 3. All right, now we'll evaluate the magnitude of RP, which is this vector right here. So we'll do the square root of 4 squared plus 4 squared plus negative 7 squared. Would you believe that works out to be the square root of 81, which is of course equal to 9. And 9 is actually 3 times 3. So this is 3 times the magnitude of vector RQ. So we have shown the condition in the question. RP is 3 times as long as RQ. Okay, up next, this is a bit of a visual question, so it's kind of hard to do on a PowerPoint screen, so I apologize if this isn't super clear. But we have a point in 3 dimensions, 1 on the X, 4 on the Y, and 3 on the Z axis. We want to find how far this point is from the XZ plane. Okay, so the XZ plane is the 2-dimensional sheet, is the way I kind of think about it, the 2-dimensional sheet through the 3D space where the X and Z values are 0. Okay, sorry, where the Y value is 0, pardon me. The way I think about this is in 2 dimensions, the Y axis is the line where the X value is equal to 0, yeah? So the XZ plane is the 2-dimensional sheet, like I said, where the Y value is 0. So really what this question is asking us is how far from 143 to X value, Z value, we don't know what it is, but we know that the Y value needs to be 0. Okay, this will be a point on the XZ plane. So the X and Z values we don't really care about. We know that we're going from a value of 4 on the Y axis to a value of 0. So that is a distance of 4 units. Okay, again, if you have a picture of this, it becomes much more obvious. Okay, distance from the y-axis. So now we're looking at a point where it has a y value, but because we're on the y-axis, the x and z values are equal to 0. So we're finding the distance from 143 to 0 something 0. Okay, if we ignore the y's, we're really looking how far is this point from 1, 3 to 0, 0. The way we find that answer is by doing Pythagoras, or you might call it the distance formula. Either way, we're doing 1 squared, because that's how far from 1 to 0, plus 3 squared from 0 to 3. Doing the square root of these plus together gets us an answer of the square root of 10. Okay, so the y-axis is where the x and z values are 0. Because that's in 2 dimensions, we've got to do a distance using Pythagoras, essentially. All right, I hope that made some sense. Apologies if it didn't. Ask your teacher. Example 4. We have two vectors where the acute angle between them is theta. We want to find the value of sine 2 theta. Okay, when I see a question mentioning the acute angle between two vectors, I immediately write down my angle between two vectors formula, which looks like this. Okay, we had this earlier in the lesson, but we just rearranged it to make cos theta the subject. Okay, so for our formula, we're going to do the dot product on the top. So we're going to do 1 times 2 plus 2 times minus 4 plus 2 times positive 4. So there's our scalar product on the top. On the bottom, we're doing the magnitudes of the two vectors and we're multiplying them together. So we've got 1 squared, 2 squared, and 2 squared here. And we've got 2 squared, 4 squared, 4 squared here. Okay, on the bottom, that works out to be a value of 3 and a value of 6. So we end up with a 2 on the top and a 3 times 6 on the bottom. So we get 2 over 18, which is 1 over 9. Okay, so we know the value of cos theta is equal to 1 over 9. However, the question was asking us to find sine 2 theta. All right, if you are a gun at the Extension 1 course, you probably already know that the expression for sine 2 theta is 2 sine theta cos theta. Okay, this is year 11 content, so hopefully you've seen that before. We have cos theta, we are trying to find sine theta. Okay, so when you are given one of the trigonometric ratios and you're trying to find the other one, the easiest way to do that is with a little right angled triangle like this. All right, this is going to be my triangle where the angle is theta. And now because cos theta is equal to 1 over 9, I know the cosine fraction is the adjacent side divided by the hypotenuse. So I can write this as 1 and this as 9. Now if I do a cheeky bit of Pythagoras, I can do 9 squared take away 1 squared, which gets me 80. So this side length right here must be the square root of 80. The reason I did that is because now I can find the value of sine theta by doing opposite over hypotenuse, which is going to be root 80 over 9. Okay, I also know that sine theta will be positive because the question said that the angle theta is acute. So you don't have to worry about negatives or quadrants or anything like that. Okay, so we have sine theta, we have cos theta. Now we can multiply them together and we end up with, is that right? Doesn't feel right. 9 times 9 is not 18. Imagine that's an 81 and then this is a right answer. Whoops. Okay, so this will be 2 root 80 over 81, which will simplify to something that's not 4 root 5 over 9. I apologize. Will I go back and edit this? Very unlikely. Very unlikely. Okay, example 5. Find a unit vector which is perpendicular to both u and v, where u has a x value of 1, a y value of 1, and a z value of 0. And vector v has an x value of 1, a y value of 0, and a z value of 1. Okay, so let's call our vector a, b, c. Okay, a on the x, b on the y, c on the z. Just a generic vector. Now, we know if it's perpendicular to these two vectors, perpendicular vectors have a dot product of 0. Okay, again, that's a result that you would have explored in Extension 1. I'm just reminding you. So we know that if I did ABC dot product with vector u, it should give me a value of 0 because the vectors are perpendicular. Likewise with v, if I do the dot product of ABC with 1, 0, 1, it should get me an answer of 0, perpendicular vectors. Okay, and the other bit of information we have about our vector that we are trying to find is that it is a unit vector, which means that the magnitude, so the square root of a squared, b squared, c squared, plus together, should be equal to 1. All right, we're going to turn these three facts into three equations that we are going to try and solve simultaneously to figure out the values of a, b, and c. All right, so our dot product, on the left, we get a plus b plus 0 equals 0. So we just have a plus b equals 0. For the middle one, we have a plus c is equal to 0. And for our our magnitude, we have a squared plus b squared plus c squared is equal to 1 squared, which is of course just 1. All right, now combining these three equations together, what we can do is take the first two equations, we can rearrange them to get values for b and c, and we can substitute those into our third equation. So we're going to rearrange this and say b is equal to negative a. We'll say c is equal to negative a. And now if we substitute these two into here, b squared will become negative a squared, which is positive a squared. Likewise for c, we'll sub in minus a, and then c squared will become positive a squared. So we end up with a squared plus a squared plus a squared is equal to 1. So we get 3a squared is 1. We can divide by 3 and then take the square root, and we end up with a being equal to positive or negative 1 over root 3. Now, because b and c are the same thing as a but with an opposite sign, if we take a to be 1 over root 3, it means that c and b will be negative 1 over root 3. So writing my answer, I'll have a as positive, b and c as negative, but because it could be plus minus, I'll put a plus minus out the front of my vector because we have two possible answers, one going up and one going down. All right, wonderful, no mistakes that time. I'm on a roll. Example 6. We have two vectors, we've got a and we've got b, where the y component, which is m, is unknown, but it is an integer. All right, cool facts. The projection of a onto b is given by this little vector here, hence find the value of m. Alrighty, let's jump in, shall we? So let's start off with our projection formula from earlier in the lesson, this guy right here, projection of a in the direction of b, or otherwise known as projection of a onto b. All right, let's chuck our two vectors into this formula and just sort of see what happens. All right, on the top, we've got the dot product, which is going to be 2 times 1 plus minus 3 times m plus 1 times minus 1. So we get that on the top, okay? 2 times 1 minus 3 times m and then 1 times minus 1. On the bottom, we have the magnitude of vector b. So we have 1 squared plus m squared plus negative 1 squared. That square root is going to get squared away because that's what the formula says. And then we're multiplying this number by vector b, which is 1, m, and minus 1, which we can see in the question as well. Okay, our expression out the front works out to be 1 minus 3m on the numerator, and on the denominator we have m squared plus 2. Now, we just figured this out using our formula to be the projection of a onto b. However, the question says, hey, this right here is the projection of a onto b. And we're saying, well, if this is the same thing as this, and obviously the thing in the brackets is the same, we can compare these two and say the thing out the front involving all these weird looking m's must be equal to negative 11 over 18. So there's the equation we set up. We say, all right, 1 minus 3m over m squared plus 2 must be equal to negative 11 over 18 because this is the same thing as this. Okay, now we have a cool little equation to solve. So I'm going to multiply the 18 across the left and multiply the m squared plus 2 across to the right. Now expanding everything out, we get 18 minus 54m on the left, and we get negative 11m squared minus 22 on the right. I can see this is a quadratic equation, so I'm just going to chuck everything over onto the left-hand side, and we end up with 11m squared minus 54m plus 40 equals 0. Okay, I'm going to assume that if you're an Extension 2 student, you pretty confidently know how to solve a quadratic equation, so I'm not going to go through this in great detail. I'm going to jump straight to the answers. You can factorize, you can use the formula, or you can just guess and check for 100 years. You'll end up with m equal to 10/11 or m equal to 4. Now, only one of those answers is valid because the question specified that m is in fact an integer. So it's not the 10/11, m must be equal to 4, and there is our answer. All right, what a ride. I love quadratic equations. For part B, we have the components. We want to find the component of A that is perpendicular to B. All right, let's talk about what that actually means. Let's say these are my two vectors, A in red and B in blue. Now, a common practice in physics or in mathematics is called splitting a vector into components. Quite often we split them into vertical and horizontal components, but sometimes you can split a vector into components where one of the components is in the direction of another vector. So if we look at this part right here, we're splitting A up into this red line right here. So this section of A that's going in the direction of B, we call this the projection of A onto B. Okay, it's kind of like how much of A is going in the direction of B. This will make more sense when we talk more about forces later in the course, but for now, just trust me, this is what it means. So the component of A that is perpendicular to B is this leftover part that completes the right angle triangle here and makes up vector A. Okay, so what this question is asking us for is find this dotted blue vector, which I'm going to call V. Okay? Now, we can find this pretty easily because we know what the projection of A onto B is. We got that in part A, and we know what the vector A is. It's from the question. And we also know that if I did the projection plus vector V, this would be equal to vector A. Okay, because these are the two components. If you add them together, you get the vector. So we can say that projection of A onto B plus vector V, which we're calling this one here, this is equal to A. We can rearrange this equation and do vector A, take away the projection of A onto B, and this will get us the perpendicular component. Okay, we have our value of, our vector A from the question. We have our projection from part A, and working all this out gets us some pretty gross numbers, but here is our answer for the perpendicular component of A in the direction of B. Okay, fantastic. Finishing off with an HSC question from 2020. It's a band 3, so it's not super challenging. I think it's pretty achievable for most students. We have two vectors, u and v. Question is, v has an unknown x component, which is p. Question is, what are the values of p such that u minus v and u plus v are perpendicular? Highly encourage you to pause the video and have a go at this one by yourself because it's not super challenging. I think you'll be able to do it. All right, but just in case you don't believe that I can do it, I'm going to do it for you right now. So here is vector u minus v. So minus 2 minus p, minus 1 minus 1, and then 3 minus 2 gets us u minus v. Here is our vector for u plus v. So we have minus 2 plus p, we've got minus 1 plus 1, and we have 3 plus 2. All right, now if these two vectors are going to be perpendicular, as we saw before, perpendicular vectors have a dot product of 0. So we can set this dot this equal to 0, and now we can make up a little equation to solve. So we have minus 2 minus p multiplied by minus 2 plus p, plus 0 plus 5 is equal to 0. We can expand this quickly with a difference of two squares. So we have 4 minus p squared plus 5 is equal to 0. Solving this, we end up with p squared equal to 9, which tells us that p must be equal to positive or negative 3. Well done if you got the same answer as me. All right, that'll do it for today. Thank you so much for watching along and hopefully learning something, maybe. Here's some recommended exercises for my class, and if you need any help or further questions, as always, please let me know. Catch you guys in the next one. Bye for now, not forever.